ANOVA. Let's go to chapter 24, ANOVA. I'm going to go up to search, chapter 24. And here we get to the section on analysis of variance. And I think this was the one where we actually spent a lot of time on exactly this chapter. Remember, this is exactly the example that I talked about in the lecture, was the chow versus restricted access to cafeteria food and extended access to cafeteria food. So we talked about this whole example in class. And we use this as our way of understanding it, comparing means. Here we have the null and the alternative, the null hypotheses for the different tests, right? And it talks specifically about, too, the weakness of doing 3 t-tests, right? Why we don't do 3 t-tests, why we do an ANOVA instead, right? We can't safely compare many groups by doing tests or confidence intervals for multiple tests because it actually inflates the p-value. This is the problem of multiple comparisons, which is why we do an overall test and then do a Tukey's test where the p-value is corrected for multiple tests. And it describes all of that here in this chapter. It describes all of this in this chapter. We also talked about the fruit flies. Wait, no, we talked about the fruit flies in a different chapter. This is about if fruit flies sleep. So all of these, that gives you loads of examples. It's going to help you so much to read through these chapters. You're going to understand it so much better. I know you understand it now, but you're going to understand it better once you read through all the chapters carefully and make sure that you can answer the questions at the end. You see there's loads of data for people who want to do extra credit to make cool labs about that I can use for other classes. It shows you how to interpret the output, talks about the F distribution, the degrees of freedom. And I think some really interesting examples, like about logging in the rainforest. Again, it gives you the conditions and the hypotheses. It states them all. It explains the math. It's exactly the same as what I presented in the lecture, but it's putting it all in one place. So you don't have to go to all the different lectures. You can just read the book. ANOVA calculations. But if the lectures are helpful, you can look at those too. I hope they are. You can watch all the videos again on like 3 times speed. Here's the summary. If you want just a quick review, you think, oh, I kind of get ANOVA. Let me just read the summary. I'll just go down to the chapter summary, read this, bullet points, boom, 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 right? Okay, refresh your memory, and then go down to the check your skills section and look at these questions. The purpose of analysis of variance is to compare the variances of several populations. It is analysis of variance. That could be possible. Let's see what else it says. B, the proportions of successes in several populations. Well, success is great. How about the means of several populations? Oh, yeah, that's kind of like the t-test where we're comparing means, but we had more than 2 groups. Yeah, that sounds right, doesn't it? How about the alternative hypothesis for the ANOVA F test in the previous exercise is? Now, we have gone over hypotheses over and over and over during this class. So I probably will expect you to be able to state null and alternative hypotheses, or at least identify them, right? So if you look at this question here, a study of the effects of smoking classifies subjects as non-smokers, moderate smokers, or heavy smokers. The investigators interview a sample of 200 people in each group. Among the questions is, how many hours do you sleep on a typical night? I guess they want to know if there's a difference in the amount of hours slept, depending on how much people smoke. And if you think about that question, the alternative hypothesis for this ANOVA would be the population mean hours of sleep in the groups are all the same. Would that be the alternative hypothesis? That sounds like the null hypothesis to me, right? The null is like everything's the same. The population mean hours of sleep in the groups are all different. Kind of, that's like saying they're all not equal to each other. I don't know about that. How about the population mean hours of sleep in the groups are not all the same? So at least one of these things is not like the other. Does that sound more familiar? Right? One of these means is not equal to all the other means. We don't always know which one. And then you could look at a dental study evaluated the effect of tooth etch time on resin bonding strength. A total of 78 undamaged, recently extracted first molars, baby teeth, were randomly assigned to be etched with phosphoric acid gel for either 15, 30, or 60 seconds. Composite resin cylinders of identical size were then bonded to the tooth enamel. The researchers examined the bond strength after 24 hours by finding the failure load in megapascals for each bond. Here are the summary data and ANOVA table for this experiment. There were 3 treatments, 15, 30, and 60 seconds. What is this N? Any questions on what N means?
I don't know what it is.
Number of samples. N is number of samples. What about X bar? We know what X bar means, right? It's the mean. That's the mean. And the symbol here, S, even if you didn't know, you might want to take a guess. Well, let's see, what are the 3 things that we're usually using to try to analyze the data? We want to know something about the number of samples, the mean, and the amount of variation there is. And in this case, we're measuring variation as standard deviation of the sample. That's S, standard deviation of sample. So we've got N, number of samples, X bar, mean, S, standard deviation of the sample for each one of these. And then we have the ANOVA table. You will have to understand how to interpret the ANOVA table. This ANOVA table is pretty straightforward. It doesn't include some of the other stuff that we get when we look at it in R. It's pretty simple. It just tells you the source. In this case, we just have one X, which is etch time, right? The degrees of freedom is 2 because we have 3 treatments. So for etch time, number of treatments minus 1. And the sum of squares, the mean square error, F. F is our test statistic. It's our test statistic. And then here's our p-value, right? Right? This is how you look at it. Make sure you understand how to do this. Read through the chapter. There's loads and loads of examples that you can use to make sure you really understand how to interpret these tables. And then you can look at this question here. The most striking conclusion from the numerical summaries for the 3 etch times is that A, there appears to be little difference among the etch times. Wait a minute. The means are 4.49, 6.98, and 8.48. Oh, it seems like there's some differences. I wouldn't say that A doesn't sound right. How about, scroll back up to the top here to get the other possible answers. Come on, up, up. B, on average, failure load increases with etch time, or On average, failure load decreases with etch time. So you look at the data, you're like, okay, here's our failure load by etch time. What's going on here? No difference, increasing, decreasing. Then the conclusion of the ANOVA test is that, right? So here's where you look at that table over here to look at the conclusion for the ANOVA test. The conclusion for the ANOVA test is that A, there is quite strong evidence, P equals 0.0002, that the mean failure loads are not the same in all 3 etch conditions. B, there is quite strong evidence, P, all that stuff, that the mean failure load is much lower for 15 seconds of etch time than for any other 2 etch times. And C, the data give no evidence, p-value, to suggest that mean failure loads differ among the 3 etch times.
A.
A, right? Strong evidence. They are different, but we don't know which one yet. Great. One more thing you also want to pay attention to that comes from this table is looking at the standard deviation. So looking at the standard deviations, we have 2.28, 3.15, and 4.17. Remember, the rule of thumb is that the largest standard deviation has to be less than or equal to the smallest twice the smallest standard deviation. So it's got to be 2 times the smallest one, right? 2 times the smallest one should be less than or equal to the biggest one. So if we have 2 times the smallest one, 2.28 is about 4.6 or 4.56, right? And the biggest one is 4.17. Let's see this question after checking the condition that all populations compared have the same standard deviation. You decide that this condition A is not met because the sample standard deviations are too different. B is not met because we don't know the population standard deviations. Population standard deviations, again, we're not looking at those, we're looking at the sample standard deviations. C is met because the sample standard deviations are similar enough. The largest one is less than twice the smallest.